So the idea of a limit is foundational to everything we do in calculus. You can't do calculus of any kind without understanding what a limit is. And the limits weren't really even developed. The Greeks didn't have any idea of limits. The Mayans, who were wonderful mathematicians, also did not have any way to express a limit. We live in a world of limits. We have speed limits in our life, and there are consequences if you go over. We put limits on our little children, on our toddlers, like this is, you may not touch the stove, that's a limit. You may not go in the street, that's a limit. But why are those limits set up? Safety, usually. Okay, it's usually to keep you from, keep you safe, okay, and doing something stupid. I mean, now you're not gonna get nothing physically is going to happen to you if you violate one of the rules of math, but your answer will be completely the wrong thing. So limits are set up for you to help keep you safe from making mistakes mathematically as well. Okay. I am a huge stickler when we are learning limits about writing things properly. You would never dream of turning in, well, maybe you would, an English paper with no punctuation. I mean, maybe you would dream of doing that, okay? But there would be consequences, and the person who's reading it would have a difficulty understanding it, and you would lose points for formatting. The same thing is true in math. Our punctuation are parentheses and equal signs and things that are written in the right place. And so just like an English teacher would look for capitalization and quotations in the right place and citations written correctly when you guys do, you're citing your sources, just like an English teacher is going to do that, I'm going to look for the same thing. Okay, I'm going to train you and drill you to have equal signs properly and parentheses properly, all of this, so that I don't want you to lose ticky-tack points on the AP exam. Okay, that's why I want you to get into good habits. Okay, the way we read limits out loud. Okay, the notation is LIM. That is the abbreviation for limit, but when we read it, we don't say lim, we say limit. X approaching C is how we read this part of it. Okay, not X arrow C, it's X is approaching or getting close to C. Okay, it would be like if you were driving in your car and your rear view was telling you when you were backing up, like it's beep, 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 like you're getting really close. Okay, we are approaching something that could be dangerous, and so we want to be careful about that. And then we equal, and then this L, capital L, is the limit, but we don't necessarily ever get there. You might not ever touch that limit. You might get really, really close, or as close as possible. Okay, if you ever had an annoying younger sibling in the back seat of a car, and they're like, he's touching me, and you're like, I'm not touching you, I'm not touching you, I'm not touching you, I'm not touching you, right? Pushing the limit and just being super annoying about it. Okay, that's the same. It happened in my car all the time. All right, when you evaluate a limit, there's 3 ways that I want you to approach doing that. The first is direct substitution. All right, that is straight math. Okay, you just plop a number in and you work out and hopefully you come up with a number. That's one way. The next one is algebraic simplification. So that's moving in, of course, into algebra. And the third way is going to be graphical, and that's going to move into some geometry. So calculus really does take all the branches of math, okay? You learned arithmetic, you learned how to add, subtract, multiply, divide, okay? And then you learned algebra to do it with letters, and then we taught you geometry, and you did more algebra. Okay, but we're going to use all the math things together when we do our limits. All right, so here's an example of direct substitution. All right, it's where you're given a limit, and we're saying if x approaches the number 5, what will the function approach? And so we use equal signs to show that we're working mathematically. Okay, we're working numerically. So we're going to take the number 5 and just drop it right in. 4 parentheses 5 squared minus 2 parentheses 5 plus 6. This is straight mathematics. It's just numeric evaluation. You always use an equal sign every time you move to a new step. So we've got 4 times 25 minus 10 plus 6. So 100 minus 10 plus 6. Answer is 94. Okay, when you do direct substitution and it actually works, that means this function has achieved its limit. It has a closed hole at 594. So 5 for x, 94 is a point. And it's a point that exists on the function, and it is not an asymptote. It's not an open hole. It's an actual point you actually got there. Direct substitution is the easiest way.
96.
Not right, thank you. See, I said it was the easiest way. It's the one I made a mistake on. Okay, next one. Direct substitution. We're going to try dropping the number 0 and seeing what happens. So again, using equal signs, I will take off if you're using arrows or if you're not using anything at all. So the numerator would be 1 plus the sign of parentheses 0 over the cosine of parentheses 0. So I always use parentheses as good form when I'm doing substitution. Then I know my trig values. I know that the sine of 0 is still 0, but the cosine of 0 is 1. And then I get 1. So that means the point 0, 1 exists on this graph. Okay, these are examples of limits where substitution works. Now, because this is the easiest way, it doesn't happen very often. Most of the time in calculus, it's not going to work when you plug it in. Substitution will not work, which is why we need other ways to do it. Any questions so far? All right, here's something where substitution will work, but you need to understand what this notation means. The brackets have a special meaning. They are a special type of graph and a special type of rule. Just like when you were in elementary, you were first introduced to the radical sign. And what does a radical sign mean? And then later you were introduced to the absolute value sign. And the absolute value sign, what does that mean? Here now we're introducing you to the idea of a bracket and what it means. And the other thing that you're going to notice, which is different, is the idea of a 1 plus and a 1 minus. In this problem, a 1 plus is not the number 1. It's a number that's slightly higher than 1. Okay, how much higher? Doesn't really matter, but it's slightly higher than 1. So think about 1 with a bunch of zeros after it. So what this would turn into in direct substitution would be bracket 1.00000 dot 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 dot, a bunch of zeros, and then 1. Okay, it is slightly higher than 1. What the brackets tell you to do is it's the command of round this down to the nearest integer beneath it. Okay, the nearest integer beneath it, round it down. So what is the nearest integer beneath this number, lower than this number? 1. So the answer to this is 1. Okay, it is the nearest integer lower than 1.000001. All right, so for the next question, we are not plugging in the number 1. We're plugging in something slightly less than 1. So an example of a number slightly less than 1 would be 0.999, a bunch of 999. That is a number just slightly less than 1, just a tiny bit. But the brackets tell you to round that down to an integer number that's lower than that.
0.
And so we go all the way down back to 0. The answer to that one is 0. So when you plug 1 plus into this bracket function, sometimes people call it the step function, other people call it the greatest integer function. It will round 1 plus, rounds differently than 1 minus. They don't round to the closest integer, they always round down to the one below it. Okay, so give me an example of what I would plug in for 3 minus. Okay, 2.99999 and several of those. Okay, what would the answer be to the result that's lower than that? 2. Okay, how about -1 plus? Okay, since these are negative numbers, so you got to think about your number line. Okay, Andre?
-0.999.
Awesome job. -0.999 ... a bunch of 9s. is slightly higher on the number line than -1. Now round that number down to an integer that's lower than it. -1 is lower. Okay. How about -1 minus? So something that's already lower than -1. 1.000 ... 001. That is something that is already lower than -1, because now the step function or the bracket function tells me to lower it even further. So I lower it down to -2 because I'm going down even lower. Okay, how would it work for pi? So we're plugging in something larger than pi. 3.141. Does anybody know what comes after that? 5. What comes after that? So what would be larger than pi? Would be 6, because 5, 9, 6 is slightly higher than that. What does that round to? What is the closest integer lower than that? 3. Okay, what about something less than pi? So -3.14 less than pi, but 2. That's higher, that's okay. But now round that down to a number that's still lower than that, integer-wise. -4. Yeah, it's always trickiest working with negative numbers. The graph of this, if you are interested in graphing this, it is really interesting graph. It starts at the origin with a closed circle, and it goes 1 unit and then has an open circle. And then it jumps up a unit and has 1 unit and another open circle. And then all the way, it just continues to be up 1 over 1, but it's disconnected. Goes into the negative sections as well. So that's why some people call this the step function. Your calculator can graph this, but it can't. It tries to connect them all, and it can't make open and closed circles. Pull out your calculator for a second. I want you to find this feature. Do you guys know where the absolute value feature is? The feature for this one is very near to that. So go to y equals, clear out whatever you have in y equals right now. Go to where you would find the absolute value. And then one of the options should be something called int. You have that? Okay, that stands for integer, and it means the lowest integer. So go ahead and select that int in your y equals, and then put x in there. Okay, so you're in a fresh y equals. You know where your absolute values are? Under math. Over to number. Okay, there's absolute value, there's int number 5. Okay, and put an x in there. And then if you're at Windows -10 to 10, which is Zoom 6 would do that for you, you can see that it will graph this sort of stair-step function. Okay, but it doesn't put the open and closed circles on. Is yours working? Oh, goodness. Okay, math, go over to the number. And so there's absolute value, right? But we're working with number 5 right now. And then x, and then your parentheses, and then check your window. What's your window? Oh, that's a funny window. Do Zoom 6 to get you a nice good window. There you go. Okay. All right, let's keep going. Okay, next, algebra. Tell me an algebraic rule that has been drilled into your head. Anything divided by itself? Really? Anything divided by itself is 1? Except 0 over 0. Because what's another rule that has to do with 0? Okay, anything divided by 0 is undefined. So which rule is it? You have 2 competing rules. You have one rule that says anything divided by itself is 0. But you never rule that says every time you divide by 0, you get undefined. You have two conflicting rules. They can't both be true at the same time. And they're not. This is a brand new form of a number. This particular number is called an indeterminate form. So if you substitute, and the result is 0 over 0, you say, this is an indeterminate form. It's not infinity. It's not 0. It's not 1. It's completely indeterminate. Not the same as undefined. Undefined is something different. This is indeterminate. 0 over 0, special form. And that means you need to approach this in an algebraic way. So anytime you encounter an indeterminate form, you should try the following. You should try foiling it out. Maybe that will help. You should try factoring. That might help. These are all algebraic things that you have been working on since you were in pre-algebra. You can try common denominators. That might help. And the final thing you can try is reducing. And let me tell you, in calculus, it's not going to be the calculus that's going to kill you. It's going to be the algebra. It's going to be a mistake in factoring. It's going to be a mistake in common denominators. It's going to be a mistake in reducing. It's going to be a mistake in adding. That's where you're going to make your mistakes. It's not going to be the new math that you're learning. It's going to be great. You're going to be like, I made one of these little mistakes. All right, so here's an example. Always try substitution first. So I'm going to try substitution. I put an equal sign, and I'm going to substitute in the number 0. So I get 0 plus 3, quantities squared, minus 9, over 0 in the denominator. That gives me 9 minus 9 over 0. That gives me 0 over 0. So I have an indeterminate form. Therefore, I need to go back, and I need to start over. And this time, so I'll just change colors because I'm going to try a different strategy, still equal. And now I'm going to foil this out, see if that helps me. Because I'm going back to an algebraic thing, I need to put limit. Limit is saying I have not arrived at my answer yet, and so I'm starting over. So this will be x squared plus 6x plus 9 minus 9 over x. This is all algebra. What do you notice happens when you FOIL? The 9s do cancel. And so I'm still working on algebra. My result is x squared plus 6x over x. So I tried FOILing. That was step 1. Step 2 is factoring. Okay, what do you notice you can do about factoring? Okay, I can factor out an x. As long as you're doing algebra, you're still writing limit. The equal sign comes first, the limit comes next. I'm still doing algebra. My algebra is x times x plus 6 over x. There's more algebra to be done. What can that be? Okay, the x's reduce each other. And so I reduce. I still have parentheses. Please keep those parentheses. And I've run out of algebra. I have no more algebra to use. However, now I can use substitution again. And so now I can put, as soon as you do substitution, you don't need to write limit anymore because you are actually replacing the x with the value. So 0 plus 6, and the answer is 6. So I was able to come up with an answer using algebraic techniques where originally substitution had failed me. So now let's think about the point. The point would have been based on 0 for x and 6 for y. This function will never get there. Okay, because I couldn't get there with substitution first, it will never arrive at this point. It will get very, very close, but it will never actually arrive there. It's going to be blocked by an asymptote, or it's going to be blocked by something else. Okay, let's try another one. We're moving on to the next one. All right, I'm going to try substitution first. 2 times 2 minus 4 for the numerator. 2 cubed minus 2 times 2 squared That's going to give me 4 minus 4 over 8 minus 8. So I do get 0 over 0. I've once again arrived at an indeterminate form, so I need to relaunch, reset, and I go back to the beginning, and I'm going to use what algebraic method do you think first? Factoring, yeah. What can you factor out of the numerator? A 2. What can we factor out of the denominator? An x. Not an x squared. I can't take an x squared out. I can take out an x, which leaves me with x, what? Squared minus, oh, I can't take out, sorry. I can take out an x squared, leaving me with x squared minus, sorry, x minus 2. All right, does that help me? Yeah. Oh. I saw it as soon as you raised your hand. Okay, did the factoring help me? Yes. Okay, the factoring helped me. What's my next step? Don't say cancel, we never cancel. We only reduce, okay? Okay, all right, so let's reduce and finish. Reducing is still algebraic, so I still have limit there. Now I have 2 over x squared. Now there's no algebra left, so I can go back to substitution, and I get 2 over 2 squared, which is 2 over 4, which is 1/2, which means the point 2 1/2, will I ever get there? Nope. All right, I have one other example. This example has to do with common denominators, so we want to see how that works. If we go ahead and drop 0 in, so 1 over 0 minus 3 plus 1 over 3 times 2 times 0, that gives us a numerator that's negative 1/3 plus positive 1/3 over 0. So we see another indeterminate form. So we need to reset back to some algebraic strategies. So the algebraic strategy here is getting a common denominator. And so we want to multiply the first expression by 3 in the numerator and denominator. And then we want to multiply the second by x minus 3 in the numerator and denominator so that we have a common denominator in both. So what that's going to give us is 3 over the quantity 3 times x minus 3. And then x minus 3 is our other numerator over the common denominator 3 times x minus 3, all divided by 2x. So there's quite a bit of more algebra to do. So again, every time you do an algebraic step, you're going to precede it with limit. So our numerator becomes 3 plus x minus 3 over the common denominator of 3 times x minus 3. And then we divide by 2x, which is an awkward algebraic thing to do, to have that denominator under a denominator. So remember that the rule for division is multiplying by the reciprocal instead. So what we'll do is we'll multiply by the reciprocal of 2x, which is the same thing. And that's going to be a lot easier algebraically for us. So we simplify. Our numerator simply becomes x as the 3 and negative 3 cancel each other out. Our denominator is 3 times x minus 3. And then we're multiplying by 1 over 2x, which allows us to do some reducing, which is another algebraic step. So again, we're still doing algebra. And so the limit notation continues. So now overall, we have a numerator that's 1. Our denominator is now 6 times x minus 3. And now we can finally get to the point where we can do try substitution again. And so we don't need limit notation when we're trying substitution. So we get negative 1/18, which is the value of the limit. So this function will never reach that value, but it does have a limit value. So let's just review the things that are legal to do with limits. You are allowed to add limits together. You can add and subtract within limits. So sums and differences are fine. You just add the limit values or you subtract the limit values. Totally legal in
limit world. You are allowed to multiply limits together. So their product exists and you simplify and multiply the numbers. You are allowed to do constants. So if k is a constant, you can pull it in front of the limit and then it becomes k multiplied by the limit. That is legal. You are also legally allowed to work with quotients as long as the denominator is not equal to 0. And then if both of them are equal to 0, that's when we saw the indeterminate form. So just some things you are legally allowed to do in math. So that would lead you to some kind of sample problems, like asking here, can you subtract? And that's a legal thing to do in math. We can subtract the limits of f and g. So that would be 4 for the limit of f, minus -1 for the limit of g. So that would be 5. The next question, you've got a scalar multiplication. So the 2 can come out to the front. That's legal. And then are we allowed to square things? Well, squaring is just multiplying something by itself. And products are legal. And so we'll have 2 times -1 times -1. So 2 as our result. Are we allowed to subtract and divide? Yes, as long as not any of those values are 0. So we'll have 3 minus -1 divided by 4. So that will give me 4 over 4 or 1.